Hi everyone, welcome to this video where we're going to be talking about concavity and inflection points. So whenever you're in a physics class and they're discussing optics, lenses is one of the topics that you might cover, and you find that a lens is either concave or convex. And so here in orange we have examples of convex lenses. So they're like poofed out a little bit in the middle. In blue, we have concave lenses. Two examples of those. And I find concave easy to remember because if you can now imagine just a lens that's like very, very, very concave, it might start to look like the cave in like a cliffside as being concave, right? Anyways, that's how I sort of remember this idea. But anyways, make sure you kind of get the idea of what we're talking about versus concave versus convex. But anyways, what we're talking about today in math terms is concavity. And in math, we talk about places where a curve or a function is concave up or concave down. And so remember this concave lens. And think about, is this face facing up or down? And basically, if you're taking a look at this blue curve, which represents some function, what you want to identify is an interval over which this function is concave up and an interval where it's concave down. And you can think about this for yourself for a moment and try to come up with your own answer. But here, I say that this is concave up. Wherever it looks like, it might hold rainwater. If, you had rain falling from the sky, this little portion of the graph seems like it might actually hold some of the rainwater, and so that's why I'm calling it concave up. And this lasts over this interval. The interval from 0 up to positive infinity. That interval is concave up for this function in blue. So where is it concave down? Well, this is concave down over the interval from 0 to negative infinity. Or if I'm going to write this interval properly, I should write the interval from negative infinity up to 0. It appears to be concave down. Right. So it looks like the same sort of bowl shape, but then just pointed down. So hopefully, this is the easiest example for which you can see concavity in action. So hopefully we're getting the idea from this blue curve before we move on to harder examples. So let's look at this red curve now and determine when are we going to be concave up and when are we going to be concave down. Well, it's much more difficult to see in this red curve because we're increasing everywhere on this red curve, right? There's not really a place where it looks like this curve might hold rainwater, except that doesn't mean it's free from any sort of concavity. It turns out that this red curve is concave down over the interval from 0 to positive infinity, and it's concave up on this interval from negative infinity up to 0. And even though it's not as dramatic, it's not as drastic, hopefully you can still see why I'm saying that this is concave up and concave down. The curve seems to be curling down in this purple region, and in this blue-green region it seems to be curling up a little bit. Whereas over here, this blue curve seems to be curling up when I say it's concave up. And as I'm reading from left to right, it seems to be curling down whenever I say that the curve is concave down. And so again, this is just two examples. I'm trying to illustrate to you what it looks like to see concavity, whether it's concave up or concave down. And to be more specific about what we mean, we have some formal definitions here. It turns out a function is concave up by definition if the second derivative is positive. So I'll write that out. Second derivative, I'll just leave it like that, is positive. That implies we're talking about concave up. And likewise, we say that it's concave down if the second derivative is negative. So negative means we are concave down. Now, an inflection point, very important word. An inflection point is a point where the function goes from concave down to concave up, or where a function goes from concave up to concave down. That's that one point where we switch is called the inflection point. And for a function with a continuous second derivative and an inflection point, we find that the second derivative is always 0 in that case at an inflection point. However, not every point where the second derivative is 0 is an inflection point. So if you have a 0 second derivative, that means it can be an inflection point, but not necessarily. If you have an inflection point, you're going to find the second derivative is 0 whenever we have a smooth function. Now, let's look at some examples. In my instructions here say, find the intervals of concave up and concave down. Then we want to find the inflection points. And then lastly, we're going to notice any points where we have a 0 second derivative that isn't an inflection point. So sort of decoys in a way. So let's first take the first derivative here. So bringing down the 4, that maybe gives me 2x cubed minus 2x. And the second derivative here is going to be 6x squared minus 2. And to find the possible inflection points, we're going to start off by noticing the places where my second derivative is equal to 0. So in other words, what value of x gives me a second derivative equal to 0? Those would be the x values, x equals plus or minus square root of 1/3, or 2/6. And we'll see, are these inflection points? Well, let me just take a random value of x and plug it in here. So like, what if I take the second derivative and I evaluate it when x is equal to 0? Well, that second derivative would be 6 times 0 squared minus 2. So 0 minus 2 is negative 2. So in between these two inflection points, it looks like I have a negative second derivative. Or I should say in between these two potential candidates for inflection point, just places where the second derivative is 0. Okay, then let's try evaluating that second derivative where x is larger than 1/3, or the square root of 1/3 anyways. So like when x is equal to 1, this is 6 times 1 squared minus 2 equals 4. And since the second derivative is positive, we know that we are concave up outside of this range. And so these really are inflection points. And I know that because I'm switching concavity on either side of those places where the second derivative is 0. And so that curve I just worked through, y equals 1/2 x to the 4th minus x squared. That's represented by this purple curve here. So at the point where x is equal to square root of positive 1/3 here, and this point where x is equal to negative square root of 1/3, this are my two inflection points. And here, where x is equal to 0, we are concave down. And then over here, I'm going to be concave up. And over here, I'm going to be concave up. And you can get that. You can get that the concave is up just by plugging in like x equals 1 and finding out the second derivative is positive there. Okay? Next example. Let's take a look at this one. Y is equal to 1/3 x cubed minus x. So let's take the first derivative and we find this is equal to x squared minus 1. Second derivative tells me that that is 2x. So my inflection point, or my candidate for my inflection point, is going to be at x is equal to 0, because that's what would make my second derivative 0. So let's try x equals 1 in the second derivative. Then my second derivative here will be 2 times 1, which is 2, which is positive, so we are concave up. And then let's also try x equals negative 1. And when I try that, my second derivative is 2 times negative 1, which is negative 2, so that means I'm concave down. So since I'm going from concave up to concave down, that's an indicator to me that this candidate inflection point really is an inflection point. Right? And an image of this curve with this formula is this blue curve, and you can see I'm going concave down to concave up at the point x is equal to 0. So that must be my inflection point. Okay, new example. Let's look at this point. And if I take the first derivative, this will be 4x to the third. If I take the second derivative, this is going to be 12x squared. So setting the second derivative equal to 0 gives me a candidate inflection point, something that might be an inflection point whenever x is equal to 0. Putting in x equals 0 is going to give me a second derivative of 0, so that might be an inflection point. Of course, it might not be either, but let's see if it is by trying x equals positive 1, because that's a little bit to the right of my candidate inflection point. And so in that case, f double prime evaluated at 1 becomes 12 times 1 squared, which is positive 12. So we are concave up there. And then let's try x equals negative 1, because that's a little bit to the left of my candidate. And if I evaluate f double prime of negative 1, this will be 12 times negative 1 squared, which is still positive 12, which is still concave up. So I do have a place where my second derivative is 0. So I do have a candidate for an inflection point. But since we found I'm going from concave up to concave up on either side of that candidate, this is not really an inflection point. Okay, so there's some places where you can have a 0 second derivative, but it's not really an inflection point. And so an illustration of the curve x to the fourth is in orange here. And so here is where I had the candidate inflection point. That wasn't really an inflection point. It was just sort of a decoy because I'm concave up everywhere, right? This remains concave up on either side of that point. And I said, maybe this was an inflection point because f double prime of 0 was 0. But again, it turned out to not actually be an inflection point. Okay. One more example here. I have f of x equals natural log x. So if I take the first derivative of natural log is 1 over x. Take the second derivative, and remember that 1 over x is like x to the negative 1 power, so this becomes negative 1 over x squared. If I wanted to set this equal to 0 to find my inflection points, you're going to find that there's no value of x that you can choose that would ever generate this, right? And since there's no value of x that would solve that equation, there's no solution, that means there's no inflection point. And to illustrate this curve, the natural log curve, I have it in green down here. And notice that over the entire domain of the natural log function, we're sort of always curling down. So this is concave down everywhere you look. And so that's why we say there's no inflection points. There's no points where the second derivative is 0. There's only points where your second derivative is negative for the natural log function. Okay? Hopefully this helps you out, and I'll see you in the next video.